Hello, electronic circuits, analog integrated circuits. In this video lecture series, we are going to study the basic concepts of amplifier, some parameters related to amplifier, such as what is input resistance, what is output resistance, why it should be high, why it should be low, and why the study of this analog integrated circuit is important. Then we'll define some basic things as a prerequisite to understand the circuits of operational amplifier. Then we'll study the op-amp's introduction in this video. So let us begin. Why this study of this op-amp or analog integrated circuit is necessary? To see the world around us, the physical world, such as light intensity, temperature, pressure, sound, humidity, velocity, so many physical quantities which are the part of our day-to-day life. Okay, they are analog in nature. They will be with us if you use any kind of sophisticated digital systems. But to detect these physical quantities, to convert these physical quantities to electrical signal, electrical voltage, or the discrete nature or digital systems, we need front end electronics, and this operational amplifier is an integrated part of front end electronics. There will be the circuits always in the front end electronics. Without that, we can't sense the outputs of transducers, sensors, and the audio outputs from microphones and so many transducers which we use in robotics, in PID controller design. So, most often, the characteristics of these signals are need to be processed and manipulated. So there are two kinds of amplifiers, okay? Linear amplifiers and the non-linear amplifiers. Later we'll define what is linear and what is non-linear amplifier. So we need to increase the amplitude, or we have to change the phase of such detected quantities which are coming from the sensors or transducers. As digital system is having front end, so there you will find the analog to digital converter. So analog to digital converter to facilitates the conversion of analog to digital, and we obtain input to the sophisticated systems like sensors and AI, and these quantities become discrete. Again, these quantities are converted back to the analog domain by using digital to analog converter. Okay, this is the different topic, but we are going to focus on the analog quantities and the circuits which process the analog quantities. Okay, and these amplifiers handle weak levels. Okay, so according to the requirement of the what we have to increase actually. Okay, suppose we want to increase the voltage of such output, such sense the data, such sensed analog quantities, so it is called voltage amplifier. If you need to increase the current of that quantity, it is called current amplifier. If you need to enhance the power, increase the power of the sensed signals, it is called power amplifiers. So it is a vast study in analog electronics, using the design using the bipolar junction transistors, design using the MOSFETs, and design using the op amps. Okay, so let us begin first with operational amplifier. We'll try to understand some basic quantities, parameters before starting the actual study of operational amplifier. Okay, so here there are some general terms we are going to toss in the study of op amp. And the first question, when we are defining the ideal characteristics of operational amplifier, so there we'll find one quantity. Input resistance of voltage amplifier should be high. Okay, whenever we say input resistance is infinity, ideally, okay, why it should be high and why output resistance should be low? These are the two questions. Okay, so there in op-amp, we don't have scope to, okay, derive the equations, but before that, we'll understand from the two-port representation of amplifier using Thevenin's theorem. So this is what? This is Thevenin's equivalent circuit of amplifier. in which we have the voltage Vi, AVI, R0 and I1. Okay, so from these things we'll understand what is the effect of input resistance, source resistance on this input quantity Vi, and what is the effect of this R0 on this output voltage. So how these values matter in deciding the gain of this amplifier. Okay, so actually there are two parts. So this is the input side. So this I'm going to mark this, and this is the input side, which includes the input resistance of the amplifier. And this portion, so this is called source, from where we are getting the input AC signal to be amplified. And this Vi is the actual input to be amplified coming from the source. And this source, Rs, is the internal resistance of source. It is not part of the circuit. Okay, and this is the I1. And let us redraw this and use voltage divider network and get the equation and try to understand the concept of or effect of Ri on the input voltage. Okay, so I'm going to recreate this using a simple method. So we can redraw this as, let us, this is our source. So this is the ground and it is plus minus Vs. So instead of showing Rs here, so I'm going to show Rs here so that it will be simple for us. After Rs, there is a Ri in the loop, and here we have ground, and here is the actual input to the amplifier. So this is the simplified circuit of input side, and this is ground. So with respect to this plus and this minus, we are going to find this Vi. Okay? And the current is I1 through this. So by using voltage divider, so this is the loop. This is the loop, and here we can show this side also. Okay, this side, same thing we are showing Vi here outside. Okay, so we can develop the equation for Vi. So it is Vi is equal to, if you see carefully, this is the applied source voltage. So it is Vs, okay, into across which we have to find the voltage is Ri. So it is the input resistance Ri and the addition of total resistance. So it is Ri plus Rs. Okay. Now from this equation you can understand the both effect of input resistance of the amplifier and the effect of source resistance on the actual input to the amplifier. Let us take first condition. So let us take the Rs equal to Ri. What happens? We'll get Vi equal to Vs into Ri. So it is Ri plus Ri. So it will be Vs into Ri divided by 2Ri. So this is the effect of Rs. So it is Vi is equal to half of Vs. Okay. What it means? It means half of the source voltage will be applied to the amplifier as an input for amplification if both are having the same values. Okay. So it is not affordable. What we want the maximum voltage at the input of amplifier. Okay, let us say Rs is less than Ri, very less than Ri. So what is the effect of this? Effect of this is, so Vi equal to Vs into Ri, this one. Okay, so it depends upon the value of Ri. Okay, so Ri is more, so this quantity will be more. So what is required thing? Ri should be high. The Ri should be high. Then we'll get the maximum input to the amplifier. Got it? We got the Answer for the first question. Why input resistance of amplifier should be high in case of voltage amplifier? Okay. Now next question, we have to find the answer. Take the second loop of Thevenin's equivalent circuit. Okay. Recreating here in a simpler way. So this is our circuit. So it is plus minus. So it is AVI. It's a ground. And here we have R0. And here we have RL. So it is RL, R0, and I0 is flowing through this one current. And where is the V0? V0 is across this. Across this, we have output voltage V0. So with respect to this ground, let us write KVL for this. So what we'll get? So V0 is equal to E. So we have voltage source here. AVI is the voltage source. So it is AVI into across which we are finding RL, resistor itself, AVI RL, and it is RL plus R. Okay. What is RL? Is a load resistance. It's a load resistance. Okay. It is external thing which we are going to connect to the amplifier. That will exhibit the loading of the on the amplifier. But here R0 is the part of the amplifier circuit. Okay. So it is the DC resistance looking into the circuit from outside. So V0 is equal to V0. So depends on R0. So R0 is in denominator. If the value of R0 is high, if R0 is high, write like this, R0 is high, what will be effect? If R0 is high, V0 will be small. V0 will be small, and this is going to affect the gain. So R0 should be small. R0 should be small. Okay. What is the ideal value? What is the ideal value of R0? R0 equal to 0. There should not be any R0. Will get the maximum output voltage of amplifier. Hope I answered the second question. Okay. So what is the gain from this? So it is gain is V0 by Vi. Okay. This is the gain of the voltage amplifier. And if V0 is maximum, we'll get the maximum open loop gain. Fine. So let us write the equation for this. What is the V0 we have? We have AVI into RL divided by RL plus R0. Okay. And what is VI? VI is VS into RI divided by RI plus RS. So this is the equation of gain. We can simplify it and we can have the effect of resistors, which already we have discussed. Okay. Let us move on to the next topic. Now we have talked much about the what is the input resistance. Okay. So there comes, while writing the ideal parameters of opamp, we write input impedance. Sometimes we write input resistance. Okay. The most important is input impedance is appropriate word while defining the ideal parameters, ideal characteristics of operational amplifier. Okay. So let us understand what is input resistance. Input resistance is purely a resistive opposition offered by input terminal of the amplifier circuit to DC. Okay. And the notation is Ri, which is depend upon the Vi divided by II, input current. So these things. How many resistors are used input side? So that decides the value of input resistance of amplifier. Okay, if you change the values, so that will affect the input resistance. Okay, and input impedance. Input impedance is denoted by Zi or Zin, which is equal to real quantity R plus Jx. What is X? X is the reactance of capacitor or resistance. X is equal to, we have 1 by j omega c, and XL is equal to j omega L. Okay, it is minus j omega c, and it is the total opposition offered by input terminal of the circuit amplifier to input signal, including resistance and reactance of inductor or capacitor, depends upon which one is present. Okay, so this is the difference between input resistance term and input impedance term. Okay, let us move on to next. So what is the decibel? Okay, decibel is the measure of voltage gain. Okay, linear gain is defined by using, so this linear gain. So if AV is the voltage gain, so it is defined as V naught divided by VI, output voltage by input voltage. Okay, and this decibel gain. So decibel is 1/10 of bell. Bell is a large unit, and its 1/10 portion is called decibel. Okay, and gain in decibel, it is AV in decibel is given by 20 log to the base 10 of linear gain AV. Okay, and linear gains, A V is linear gain, suppose. So here we have two gains of multi-stage, or three gains of three-stage amplifier. So these gains are multiplied. Okay, linear gains are multiplied, while the gains in decibels are given. So these gains are added. So AV1 in decibel, okay, plus AV2 in dB, plus AV3 in decibel. If these are in decimals, these gains are added. Okay, so this is one more worth point to remember while discussing the design of amplifiers. Now current gain, what is current gain? So it is AI is I naught output current divided by input current, and it is also given by 20 log to the base 10 into linear gain. Okay, so power gain, so it is AP is the power gain. So it is output current into output voltage is output power, input current into input voltage is input power, and it is in decimal, in decibel it is given by not 20 log, but it is written as 10 log to the base 10 of power gain. Okay, so moving on to the next topic. Now here starts the operational amplifier introduction. What is opamp? Okay, operational amplifier. The operational amplifier opamp is fundamental building block of analog circuit design. The name operational amplifier originates from the use of this type of amplifier to perform specific electronic functions or operations. What kind of operation it perform in the beginning, such as scaling, summation, integration, differentiation, and so many operations were there. And these, particularly, op-amp was designed to perform these operations in analog computers in the beginning around 1947-48. Okay, but present day op-amp is built using different transistors, BJTs, okay, MOSFETs. Okay, so many things are added. Now we have most sophisticated designs of operational amplifier. Accordingly, it finds the applications in different fields of electronic, or we can say front-end electronics. So here, as a sample, I have mentioned some applications of operational amplifier. So there are so many applications of op-amps in front-end electronics. So I have mentioned few only. So audio amplifiers, headphones we are using, speakers and mobiles, active filters in earphones, okay, microphone preamplifiers, touch screen signal conditioning, battery management system. Okay, so this is the latest field. We can say it is electronic vehicle systems, or we have the batteries, okay, which are used in cars, smartphones, laptops, and all these things. So here op-amp plays an important role in this design, these things. Camera and sensor readout, audio processing engineering, drones and robotics, particularly in PID design or PID controllers of the robotics, okay, or drones, variable electronics, there are n number of mentions where opamp is used, okay, image processing, satellite communication, okay, so many things are there. These are the few out of many applications of opamp. Now, so here we have the symbol of opamp. Already I have described why it is called op-amp because of these operations. And one more thing, word to tell that the op-amp, the symbol, so this is the symbol of op-amp. Now see, symbolically it is shown like this. We can't understand the operation of actual working from this symbol. For that you have to go to the internal circuit of operational amplifier. So it is a vast circuit using 20 to 50 transistors are used. In beginning only bipolar junction transistors were used to build the internal circuit of op-amp, but nowadays MOSFETs, okay, are used to latest designs and advanced for our advanced applications. Okay, so let us understand the symbol. So here it is minus plus, and this is 1, 2, and this is 3. It's a sequence, not pin numbers. And here, so plus VCC and minus VE. These two are biasing voltages. Okay, I have shown further what are these. So here we can show the power supplies plus is connected here, it is minus. We can show like this also, VCC and VE. These are the two power supplies. Okay, and this power supply, what is this? So these are biasing voltage. So this is called biasing. As op-amp is semiconductor IC made using transistors, and to turn on semiconductor IC, semiconductor devices, we need DC voltage as a biasing voltage. These are not inputs, these are the bias voltages. Okay, and where we are applying inputs at point 1, point 2, which is called inverting input, and it's a non-inverting input. Okay, at point 3 we are taking the output. Okay, and these are the actual inputs, these are the AC inputs, V1 and V2 are applied here. Okay, and the most important thing is um, output swing. When these voltages are amplified, difference of this voltage is amplified, so the voltage swing will not proceed than this. The output voltage V0, okay, suppose here we have V0 output. So V0 output will not go beyond this. So it is minus VEE less than V0 less than VCC. Okay. So these DC voltages are important, and output swing. So this swing, so this is the output suppose. So this swing will not go maximum value of this one. Okay. So here the limitation of this amplifier. So accordingly VCC is applied. So actually VCC, okay, it's a symmetric power supply. It's a plus minus 5 volt, plus minus 10 volt, plus minus 15 volt, plus minus 18 volt, and so on. Okay, there are limitations according to the manufacturer. Now, so this is the few names of ICs, different manufacturers having different name for IC. Okay, LM741. This is the pinout, and this type of structure is called as a dual inline package. Circular, okay, different types of, according to this TO2 package is called TO T0 package is also there. 8 pin, 4 pin, okay, different ICs are available in the market. And if you go to data sheet, you will get the details of these different ICs. I have mentioned only few names of the ICs. There are so many ICs are there in the market today, and it is used according to the requirement of the circuit. Okay, so here is offset null, inverting, non-inverting is applied, and it's a minus VE and it's a plus VC.